get started then. Hey, I'm Katrina, and this is Yee, and we're here today to talk about Flyte. And as an overview, Flyte is an open source and cloud-native platform for building, running, and scaling workflows for machine learning and data processing. I'm really excited to present Flyte today and kind of walk through a tutorial of how it can hopefully accelerate your machine learning workflow pipeline development. So before we begin, just a brief history of Flyte to kind of explain why we built this. So originally Flyte was developed at Lyft, which is the US-based rideshare company, kind of like Uber. And so as you can imagine, working in this marketplace application where, there were a lot of real world mapping integrations, there was a lot of demand for machine learning models at Lyft. And as we discovered at Lyft, however, the typical model lifecycle isn't just, writing machine learning code. It starts way earlier. You ingest new data, this data gets transformed, prepared, cleaned up through ETL process. And then after all the data is structured, you compute features on top of that in order to use for model training. And that's the point where your machine learning code will come in. But even after you build and train a model, the work isn't over, and you need continuous monitoring to detect data drifts, biases, and whatnot. So even after you ship a model, it needs to be served using some kind of scalable platform that allows you to monitor its performance. So these are kind of the problems and issues that we're facing at Lyft. So we came up with Flyte in order to address this use case. We open sourced the project in early 2020, and we actually donated the project to the Linux Foundation, the AI and data track, at the beginning of this year. So kind of continuing off of our complex motivation process here, as you can see, ML and data systems are very, very complicated. And in this example, this diagram represents data flow across different systems at Lyft. And some components are here just to strictly process data that's required maybe to build model downstream. And other models are consuming data other components are consuming this data to build models, but this overall topology is quite complex. And as you can see, even here, just this example of building a pricing model for upfront rideshare prices, we consume data from machine learning improved maps, and this informs how we calculate estimated times of arrival and routes, and all this is augmented by various payment structures and incentive needs and insurance needs. So building a model, very, very complex. And even in this diagram, all these boxes are kind of just a simplification for illustrating like what building a model is. Each of these could have other connected component boxes. This isn't even a complete list, right? This is just one particular use case. And despite the specialized and diverse nature of all these boxes, the flow says all this data is actually powered by Flyte. And at Lyft, even we have thousands of unique workflows and millions of containers that get executed per month to kind of orchestrate all this flow. And we feel like we're just getting started. So kind of going back to what we talked about the typical ML model lifecycle, you can see writing a machine learning model isn't just like one kind of discrete task. There's all sorts of other like steps that come into play. You have to ingest new data, you have to transform it, you need to run models over and over again, you have to change your logic, you want to be able to go back and edit your models, etc. And when you do inevitably need to make all these changes, you don't want to find yourself, trying to like trace down code from someone's laptop or, find some like model that hasn't been running forever. So enter Flyte. So Flyte fits in here as this kind of production grade orchestration framework for data and for other ML use cases. You can orchestrate code, containers, scripts, queries across disparate systems like Redshift or BigQuery. And it does all of this with strongly typed interfaces that are defined in an agnostic declaration language, which is protobuf in our case. And we're not saying that Flyte is the end-all solution to model training. As you can tell, it only comes into certain parts of this overview or this workflow. But it is a tool that you can use broadly for data processing, ingestion, prep, model training, inference, and then further on monitoring. Great. So now that we've explained kind of where, why we developed Flyte and what it's capable of doing, let's talk about how to use it. And specifically, let's kind of go over the features to distinguish Flyte and hopefully how it can improve your ML development workflow and operations. So let's take a look here. So use cases. So as we mentioned, we originally built Flyte because of the difficulties that we face in building and deploying our machine learning models. So Flyte was designed from the ground up for ease of use. And this includes, being kind of an infrastructure less tool. So users don't have to necessarily deploy and monitor additional services in order to use Flyte. You can just have a centrally hosted Flyte platform that other users can access without worrying about infrastructure or ops overhead. So Flyte is it's just a single hosted platform. So since teams don't have to manage it, there's kind of no like concern about like again, like I said, like ops or like considerations when it comes to development. Flyte allows you to specify and customize different task resources. So if you have, say, like a GPU intensive training job that you go on to run, you can easily spec that out in your individual task definitions, and Flyte will manage scheduling and assigning your jobs where those resource constraints can be met. And Flyte is also not prescriptive, so you can run any container that you want, which means you can use any framework or any library as well too. And Flyte is also multi-tenant by design. So, it's meant to have multiple customers, multiple teams on board, and again, just be centrally managed place where individual teams don't have to worry about standing up their own infrastructure. And this comes with seamless scalability. Flyte scales horizontally, and it's easy to bring up new teams with it. We also, of course, try to design Flyte to be really accessible to use. Flyte is, I like to think, like a complex piece of software, but the user interface for authoring workflows and maintaining the overall Flyte deployment is fairly straightforward. And then finally, we know that if you're running Flyte in production, then training machine learning models can sometimes be very compute expensive. So Flyte provides lots of visibility into understanding how to control your costs, understanding resource usage, and how you can and utilization as well, so you can improve resources allocated for your jobs and hopefully save some money while you're at it. So kind of digging more into authoring specific Flyte workflows. So we started with a job, which is like, say, an individual task, which, in this case could be maybe running, a Spark query to grab training data, or, maybe analyzing data that's already been fetched. So that's kind of like the core fundamental unit of work in Flyte. And then once you have a single job, you can scale it across different input parameters. At Lyft, we broke kind of like our data into different market share regions. So in this case, maybe you would want to run the same model across different regions, or maybe with different resources, such as, say, GPUs. And then once you've kind of scaled your job and tested that it works for all of your kind of input data, you'll create a pipeline, which is basically kind of a composable graph of different tasks in order determined by say data dependencies as data shuffles between these tasks. So kind of a straightforward example here would be, go fetch your data, train a model, and then maybe calculate some performance metrics after you're done. Once you've kind of iterated on your pipeline, you can run this pipeline on demand with a different set of parameters as your upstream data changes, or maybe if you're running across, a set of different time zones, you can run this pipeline for your individual days. And then after you run it on demand, Flyte allows you to also run your pipeline on a schedule, which you can use cron expressions to tweak and denote. And then finally, Flyte also writes version results for all of your individual jobs and overall workflow pipeline runs. So all this data is accessible and discoverable after the fact. Digging kind of more into these specific Flyte use cases, let's talk a little bit about parameterized applications. So you can parameterize your experiments because literally any input can be defined for individual tasks, and this will let you, say, alter coefficients. You can analyze different data sets without having to necessarily make code changes. Just as long as your input changes, then you don't have to go ahead, kind of like re-upload or tweak your code. You simply just have to invoke jobs with different input values. Simultaneous schedules. So you can run differently parameterized pipelines on simultaneous schedules in order to collect or validate experiment data or perform A/B testing. You aren't limited to just, say, one schedule per workflow definition. Flyte UI ships with a native UI for exploring and rendering workflow graphs. You can visualize, currently running tasks, see inputs, outputs produced by tasks, use logs in order to improve your developer velocity, and this is all accessible in the console. And kind of on the same topic of parameterization, time is just a single parameter. It can be in past, future, present. You can run scheduled executions with time as an input, And you can also run a backfill job where you simply just, range across the span of dates and provide time as a singular workflow input. And Flyte is also built to be data aware. So you can track pipeline artifacts to answer, how, where, when, why was data created. And this is all tied to specific versions that are tied to specific workflow and task definitions. And finally, you can also dynamically generate pipelines. So you aren't bound to just having a static, pipeline or workflow graph definition. You can actually alter the graph structure at runtime based on different input parameters. And in fact, you can add some more regions on some specific days. In the case of the mapping use case, you can alter the shape of map generation. We also have branch nodes, so you can do things like if-else statements in order to alter the runtime execution behavior of your pipelines. So let's talk a little bit about what developing on Flyte looks like. So we designed Flyte with a few core tenets, which is that development shouldn't affect production data. So Flyte is kind of broken down into different module domains, and they allow you to sequester your pipelines, the code, and the data within them into different scopes, such as development and production. You can promote workflows across different domains, but they remain distinct concrete entities. We wrote our user-facing SDK in Python, which is kind of the lingua franca of data science. And actually, after a lot of iteration, we recently released a new SDK update, which kind of is built on top of the intuitive nature of Python and lets you adapt your existing code with minimal changes. But Python isn't the only language that you can use with Flyte. So since we're open source, we've actually benefited from contributions of Spotify, which contributed a Java SDK. And also because Flyte lets you use any container definition as an individual task, you can literally run any code in any language as part of a Flyte workflow. And testing at scale. So, you can define your Flyte workflow, test and iterate on that locally, but you can promote it onto, or you can deploy it onto Flyte after you're done and satisfied that your workflow works locally, which means that you can run your workflow with production grade resources, such as, more data or more machine learning or machine resources such as GPUs, and all this helps you accelerate your training. Like we mentioned earlier, the Flyte is data aware, which is really valuable because you can actually cache individual extensive jobs within a pipeline. So as you iterate, if an upstream task succeeded, but it was really expensive to compute, you don't actually have to keep recomputing it every time you rerun the pipeline. So Flyte will version your data according to the task version itself. So this guarantees that your tasks will always be correct, even when you enable caching and reuse them. And then let's talk a little more about maintaining Flyte. We talked about how it's kind of useful as an end user, but if you want to deploy Flyte at your or stand up a Flyte instance, of course, ops and maintainability is an important consideration. So as you mentioned, because we have this kind of notion of versioning, you can easily track all of your executions and input parameters and output artifacts across different pipeline runs. So you can kind of really determine where and why data was produced. And this is all accessible in our console, and we also have a RESTful API, which you can query programmatically. And as part of productionizing your workflows, you can also optionally add notifications that will trigger on, say, success or failure. This is really useful when you combine this with scheduled workflows because you don't necessarily have a human in the loop, and you want to page someone on, say, errand or erratic data. We built Flyte, primarily for engineers and data scientists, which means, that we expose a ton of stats so you can monitor the health of your Flyte workflows. We have different configurable log plugins which work with different cloud logging providers, and all this should make the debugging your Flyte workflows easier. And to that end, you can also use Grafana or whatever charting tool you like to use to visualize stats for your pipelines. And you can track runs independently. So you can actually go and replay pipelines, fetch and interact with this pipeline data. Like we mentioned, it's all versioned and accessible. And this lets you kind of understand what was happening, in a specific use case. Great. So reusability and shareability. So kind of continuing up that theme of version data, code is also versioned as well too. So Flyte tasks are are composed into different pipelines, but the tasks are kind of proper entities. So once you register them, you can reference them anywhere, which really helps with code reuse. So shared tasks can encompass, common functions, but they can always be embedded in multiple pipelines. And to that end, you can also share task outputs as artifacts. So Flyte, Flyte organizes, entities within, different projects and domains. So you can share across, these different projects, and say if these projects correspond to different teams, you have your, organizational boundaries within your company, but you can still reuse your code across those without necessarily breaking another team. And you can compose these pipelines or workflows, as we call them, using workflows from other teams as well too. So it's not just tasks that are shareable, but workflows as well. And a few notes on extensibility. So some of the things that we learned kind of when we first wrote Flyte, or the precursor to Flyte at Lyft, is that users want extensibility. We can't predict every single use case. And much like Airflow operators, we've kind of exposed different customizations that are available in the Python-facing SDK. So you can define tasks as simple Python functions, but you can also have tasks that span different functionalities, such as querying stasis of Spark or Hive or whatnot. You can also run your own container instead of the one that Flyte builds for you as part of your task definition. So very powerful and expressive there. But also for more complex use cases where, say, maybe you need to integrate with an external service and you want to pass, say, secrets or credentials, and you want to globally kind of control how you roll out different features to your users of Flyte, you can actually deploy backend plugins. And these are included as part of your hosted deployment, and they'll actually be accessible to all of your teams. And to that end, not only are these backend plugins, they don't only expose additional functionality, but they also kind of allow you to, stay transparently migrate vendors. Let's say if you have, plugins that query against vendors and you want to try to bring that as an in-house service, you can just do this transparently on the back end by updating your backend plugins, and your users don't have to update or re-register or do anything to change their code. Their executions will proceed normally. So in summary, Flyte is an opinionated, scalable, but not prescriptive platform, and its hosted nature makes it very maintainable. It's kind of this, disparate fabric that connects different compute technologies, and it's also extensible on top of that. It's developer friendly. It's built with monitoring and observability out of the box. It integrates natively with, open source and popular applications, and it's built for production use in industry. So, data is meant to be audible, it's reproducible, and the platform is actually built with security and authentication built in. Cool. So now that we talked about what Flyte can do, let's talk about what using Flyte is like. So here's kind of an overview of what the user journey is like on Flyte, and this should be familiar as, kind of a generic, as you integrate or as you iterate on your code kind of journey. So you start off, with an idea, and you start, defining your business logic, you iterate, you test your code locally, and then once you're satisfied that works, you'll promote it to, running on the remote Flyte platform. And, once you have a task, you'll extend that extend your job to include multiple composable tasks to a workflow, and you'll want to run that workflow for different set of inputs and repeat. And then we move on to kind of the productionization stage, which is, say, like once you've satisfied yourself that, your workflow works as intended, you'll promote that to production using, say, CI or CD, potentially add schedules that'll run your workflow routinely, or you can also execute it ad hoc, and you'll have, all sorts of monitoring and stats baked in. And after your workflow has run in production, you can go ahead and analyze your data and the results from your executions in order to, say, debug production errors, kind of reproduce the flow of how artifact data was produced. And you can also trace the lineage of different artifacts as outputs from different tasks in a different workflow. So we've kind of been using like tasks and like jobs and pipelines and workflows kind of interchangeably. So just to kind of define like the language of Flyte. So let's talk a little bit more about like what tasks and workflows are in particular. So tasks are kind of an invisible unit of computation from Flyte's point of view, and they can be as simple as, say, a container execution or remote query execution like Redshift or BigQuery, distributed Spark application. So Spark or tasks are all defined in declarative protobuf language. They're versioned, and they come with strongly typed interfaces, which allows us to catch errors faster at runtime. And they kind of are like the way we model a flow of data inside of a workflow. So tasks can be, arbitrarily complex, but you assemble them together into these kind of composable workflows, which, like we mentioned before, can be dynamic. You don't necessarily need to statically define your graph, and can be authored in Python or in Java. So here's kind of a code sample of what like writing a Flyte workflow actually looks like. So as you can see here, it's quite straightforward. All you have to do is annotate individual tasks with this task decorator. Here we're processing a pandas data frame, based on input value of, say, an integer. Once you produce that pandas data frame, then maybe you'll do some transformation on it, and then your workflow happens to, in this case, be composed of calling your two tasks in succession. Here's the Scala example down below, and then here's what the console looks like. You can see for kind of a more convoluted graph type structure, how you can overview, the state of your tasks. There's the version clearly baked in, and you can take a look at your inputs and outputs. Cool. All right, well, that was, let's take a look now, I guess, at how Flyte actually works in action. So what we'll be using for this demo is Flyte has a kind of cookbook, which is just a set of working examples that you can just clone off GitHub onto your local machine. And Flyte also ships with an out-of-the-box sandbox, which is just as easy as running a single command in order to bring up. So let's take a look at what that looks like. So here I've already brought up the Flyte sandbox. And as you can see here, I have a ton of different workflows registered. A lot of these are kind of trivial, so we won't dig into them too much, but we also have individual tasks, which you can run as, if you prefer, as opposed to writing an entire workflow. And an overview of executions. This is a fresh sandbox install, so we don't have any executions quite just yet. Great, so this is a tour of console that you get out of the box. So let's go ahead and write a Flyte workflow. So to start with, here I have this very, very trivial like Python code. Let's say that before I've even like got to the stage of writing a Flyte workflow, very simple hello world kind of example that'll combine two different strings. And we can take a look here. We can run this. Hello world, awesome. Great. So let's see how easy it is to transform this into a workflow. So I already copied and pasted a Flyte workflow here. But as you can see, what we have to do is, all we need to do is import the FlyteKit task and workflow decorators. So here in this combined strings method that I previously had, we define that as a task. Let's add some extra emphasis here. And then we have a simple workflow, which basically calls combined strings on those two workflow inputs, which are workflow string 1 and 2. And if you want to take a look, we can still run this workflow locally. Nothing has really changed. Hello world, lots of enthusiasm, awesome. So now what we'll do is we'll go ahead and register this updated workflow and give it a whirl on Flyte. So registration comes in two different flavors. And so conventionally, what you would need to do is you would want to build a container that contains all of your workflow code, and then that'll get executed when you run your workflow. But for the purpose of this demo, and also just for faster iteration, we actually have kind of like a fast process that makes the building container option not necessary. And so that's what we'll be doing here. This will just package your code and then into a tarball and then untar that archive at execution time. So let's take a look at that. You can see we have a ton of examples here, and this registration process is actually two-step. So what we did is first we serialized all of our workflow definitions into that declarative protobuf language that I mentioned earlier. And then what we do is we register those protobuf representations under a specific project, which in this case is Flyte Snacks, because we're using this cute cookbook analogy. And then upload all of those serialized entities under a specific version, which in this case is our kind of like fast determined version. Cool. So let's take a look at that new workflow. which is our Hello World workflow. And let's launch that. So hi, Eva. Let's see. So as this is running, you can see the overall workflow state is unknown while the backend is processing other workflows and going to pick up the work. We can take a look here and see this is kind of a really simple graph. We just have a single task. In this case, you just have inputs, which feeds into that single task, which produces outputs, which are outputs for the entire workflow. And already ran and succeeded, a simple example. So that is hopefully by design. You can see we have nodes, and nodes here encompass task definitions. Usually nodes correspond to just one certain task, but you can also have, say, things like map tasks or dynamic nodes, which kind of generate a sub workflow. And these are all kind of like units that encapsulate that work within the overall workflow graph structure. We can take a look here. We can see that logs were produced by our task, and there's nothing to log. Caching was disabled, but you can always enable caching if you do want to. Take a look at our inputs, our outputs. Woo, so much enthusiasm. And then here, take a look at the task definition, which represents that serialized task that I mentioned earlier. In this case, it'll show kind of metadata about what kind of SDK version I was using, unique task identifier values, and then what container image that we were using. Great. So yeah, that was kind of the Hello World demo. You will talk a little more in depth about a more exciting demo further on. So let's go back to our slides here and resume. Well, so let's talk a little bit about multi-tenancy and kind of review what we just saw in action. So entities in Flyte are organized into different projects. Like I mentioned, for this trivial example, we had our Flyte Snacks project. And then a set of domains across platform kind of further segment individual projects. So in this case, we have, say, development or production. This is useful for, distinguishing between like development and production data, but also setting up CI and CD. And then within those logical domains, we registered those tasks and workflows, which again, have these strong interfaces that use Flyte's distributed type system and are declarative. Right, and then let's talk a little bit about the registration flow that we also just observed. So what normally happens is, say you define your code in Python, we build a Docker image which encapsulates all of your code. Then we write a protobuf representing that task spec, including specific arguments to run that task within that build container image. And then we go ahead and we use that command line that I just showed to register those task definitions against the backend. In this case, that component is Flyte admin. And once your tasks have been uploaded, you can run them anywhere in the console. Your teammates can run them. And that code is immutable. And because it's version, you can always update it by writing new versions. Yeah, and I will hand it over to Yee to continue this presentation.
Can everyone see? I'm using this, yes. Cool, thank you, Katrina. I am going to, well, let's start out talking about, I'm going to talk about the dynamism a little bit. Katrina already touched on this in a couple places, but just kind of grounding this on with the concepts that we were just introduced to, the tasks and the workflows. If you think about a task function as something that will run at execution time on like a Kubernetes cluster, for instance, and you think about the workflow as the declaration of the DAG, the workflow function will run at compile time. So in the serialized steps that Katrina just mentioned, dynamic workflows are introduced by running that compile step at runtime instead. So you gain a whole lot of flexibility. You can, a node here, this guy here marked in D, can will produce an entire sub workflow effectively. You also give up some things. So you lose the ability to statically check the contents of this. You don't know what kind of structure you don't know what kind of structure this will produce. And if it says here Flyte can scale to more than 10,000 nodes, that's absolutely true. If you scale to much more than that, you do get performance degradation. So like you may inexplicably see things slow down and such. We're going to do a second demo that kind of goes over some of these things. I'm going to kind of just bring in some code and launch the workflow. And then let me see if I can. So I'm also running the exact same Flyte sandbox that Katrina was showing earlier. I brought it up earlier. As one of the other steps that I did is I already pre-built the image with the existing code. So this shouldn't take too long. The same series of steps, serializing everything to protobuf, and then shipping them up to the control plane, which you should then be able to see here. So we're going to kick off something called a multi-region house price predictor model. I'm going to launch it with some inputs, and then make this a little bit bigger as well. We're going to launch this, and now we're going to go back and take a look at the actual code. So I'm going to caveat that this is supposed to be a little bit more in the wheelhouse of what a data scientist or machine learning researcher would actually do, but this is still very much a trivial made-up example meant to demonstrate and show off Flyte, but it's not a complex machine learning task by any means. So let's just start off at the top. So basically, we're going to use a random number generator between these two things to make a just randomly generate home prices based on some hard-coded parameters. And we have a function that will take a data frame and a seed and a split and then produce 3 different data frames from the original data frame. It's going to be basically a training set, a validation set, and a test set. So Flyte has the ability to understand, like the Flyte IDL has covers the gamut of your basic primitives, but it also has schemas. So the pandas data frames are basically translated to schemas, which subsequent tasks can pull and reconstitute as data frames. And then there's a fit task, and there's a predict task. And then there is this workflow here that will generate data, split it out into 3 different components. We will fit a model to it, and then we will run some predictions on it, and we'll return those predictions. So this is not actually the workflow that is running. We ran the multi-region one. So this one has not just one location. Actually, location doesn't really matter. It's just a name. All the other, the logic is the same. But you can pretend that it wasn't. So this one will run that same workflow, but across a different number of regions. And the way it does that is with that aforementioned dynamic task. So this is, notice that these tasks in this multi-region workflow are literally just imported from the original single location house price predictor. And we do the same series of steps. So train, if my mic gets a little bit fuzzy, it's because the fan is now going because we're running these models in the background. Anyways, so the same number of steps. Generate data, split it out, fit it, and then predict. Notice that these are called parallel fit and parallel predict because the Flyte engine will run basically optimistically if there's a node in the workflow DAG that it can execute, i.e. the all the dependencies for that node are satisfied, then it will kick it off. So it ends up being automatically parallel. But in any case, going to introduce a couple things here. So first off, notice that we are taking in a list of locations and a list of locations and a list of values, and we are zipping over these and iterating over these. You can normally do this in a task. You cannot normally do this in a workflow. And I think I'm going to go back to the other slide here real quick. This gives a much more concrete example. Like this type of syntax is not possible in a workflow because in order to do the data dependency understanding in a workflow, the inputs and outputs of tasks are not your typical Python literal values. They're Flyte literal values. So something like a range, which is a Python native operator, like it would not be able to understand the input to a workflow at all. In the dynamic case, however, it can. So this produces a workflow with, if you were to give it 10 different nodes. So that's a better example for that. So basically just iterating over all these things and then producing a sub workflow, which is handed back to the Flyte engine called Propeller to run, which is, I believe, what is happening here. And it is still going, but you can see that it's launched I believe seven different things, some of which are finished, 2 of which are still running. So we'll continue to wait for that. Another thing that this has introduced is a couple additional control operators to the task. So notice we have added caching. So we've turned on caching and we give it a cache version. We are basically limiting the amount of resources that it can take. I think these numbers were set so that it runs on this sandbox environment. Hang on a second. Actually, we'll go back to that. So yeah, so the results will be cached effectively. Let's see where we are with this thing. So here, okay, so this is the parallel prediction function. There are 7 different outputs, 1 for each location. So basically, the outputs of each of the sub workflows are then reconstituted in this arrow here, back up to the dynamic node. While that's finishing up, one slide on memoization. So we basically, the primary key of caching is going to be the task signature, the inputs, and then the cache version that the user has to define, basically. Basically, we can't, like as a platform, we cannot know if the contents of your task or your function has changed. Therefore, we cannot automatically validate or invalidate a cache, right? Even if we were to look at the code, we wouldn't know if there was like a meaningful logical difference between one like Git version and another Git version. So that is incumbent on the user to understand and intelligently increment. But if you do change like the signature, for instance, then we know for sure that we should invalidate the cache. Let's see if this is done. Cool. So this was the generate stage. This was the fitting stage, and end node 2 is the prediction stage. And all these have finished, and we get some random home price predictions, which is great. Cool. Let's go through again. I'm going to make this slightly more complicated now. Let's get out of this thing. So make some changes to the code. What are we changing? Let's compare, right? Now we have the original test data anyways. Let's take the predictions. I just added a task basically. Let's take the predictions and see how far off we were. This is maybe something that you forgot to do or something. We're going to add it as an output to the workflow itself. So adding one more output. Now, let me see if I can. And just to speed things up, we're going to use the fast register construct that Katrina mentioned earlier. If you go back here and you go back to browsing your workflow, and let's relaunch, notice that we're now running the fast version. So we're going to add one more task that does the comparison at the end. So again, this is running, and then and 1 and 2. So if you hover over these things, you'll notice a little thing comes up that says output for this execution was read from cache. This was intentional. This is like a toy example where the randomness is all controlled from the seed, which we kept at number 7, which is why the first time these N0 through N2, and these nodes are renamable. Like we automatically give it a name that takes up the least amount of memory space effectively, but you can give it a more meaningful name if you need to. But these all ran very quickly because we just read the numbers from the cache, and then this is the only one though. This is only a task that was actually run. So yeah, these would be the failure predictions, which seems kind of high actually, but from the generated data. Yeah, so that covers. Let me go back to this thing. I think that covers pretty much everything here. Oops. A couple more features that Flyte Kit offers. So you can easily customize tasks to run different images. So if you have a workflow that is comprised of like some Spark tasks and some Python tasks, you don't necessarily need to have all your Spark dependencies in your Python task. So you can very easily make a smaller image for that and make a larger image for the Spark stuff and construct one workflow out of those. Output memoization we touched on. We've recently added secrets support in the Flyte Kit API, so you can pull in secrets that are mounted in by the rest of Flyte. And schema support, this is what we meant by understanding data frames. We're in the process of beefing this up as well to add better support for arrow frames. This one we touched on, this one we touched on. Actually, going back here, we don't have an example of this in the demo, but we also have conditionals. I think Katrina mentioned this earlier as well. These are in the workflow definition. So this X is less than or equal to Y. This is not spinning up a user container to run this code. This will be run by the Flyte engine itself. And X and Y here are limited. Like they have to be basically outputs of a prior task or a scalar that has been like a literal value that Flyte understands. So you cannot do something like this because the Flyte engine cannot parse that. It has no idea what the length of something is. For those interested later, well, there is a very cool, but I was told not to really talk about it too much, example code that is in our Flyte Snacks directory called merge sort. It basically runs a distributed merge sort, and you can look at it if you want. The code itself has a minor bug in it, actually, the user code, not the Flyte code. Finding the bug will be an exercise to the reader. Okay, let's talk about deployment strategies. So first off, the architecture of like just the various components. There aren't too many. There is a data catalog. This is what handles the caching that we just talked about. There is an admin. Actually, there's another one here called Flyte Console, which is a separate service for the UI. That is what actually hosts the static assets and the TypeScript and so on. There's Kubernetes and Flyte Propeller running on Kubernetes. And then we you can use things, well, you have to use things like a durable store, an S3 or GCS, a SQL database. You can add in a queuing service, and a scheduler just will support the scheduled workflows and notifications and whatnot. All Flyte tasks are run through plugins. So even the lowly Python container task has a plugin that will be called. Basically, Propeller, which is the engine, as it traverses a graph and it sees a node that is runnable and not yet run, it will look into it. If it sees that it is a task, it will ascertain what type of task it is, and then pick out the correct plugin to execute it. So in the case of a Python task, it will just run a pod on that cluster. In the case of like a Spark task, it will call the Spark operator effectively. SageMaker Batch, Amazon Batch, these are different integrations that we also have. So with that in mind, this is a rough overview of what the sandbox looks like. Sandbox just means that you can run it without contacting your infrastructure team. Like you don't need a new S3 bucket. You don't need to provision RDS because it comes with Postgres inside, a containerized Postgres as the Flyte admin database. It uses Minio as the S3, Project Contour and Envoy as your ingress, and no need to set up ELBs, CNAMEs, whatever. So wrapping all this type of deployment up and running it on K3s is what the Flyte sandbox that we've been using is. So this is the variant that you should use if you're just exploring it, just playing around with it, trying to understand it and get things running. As you move to actually deploying the next logical step is probably to run a production K8s cluster. Okay, so on some sort of a cloud provider. So now on AWS, we use Aurora as the database. We actually use the real S3 as the durable data store, and SQS and CloudWatch supply the notifications and scheduling. Notice that there are two of these little wheel icons for admin and data catalog, and only one for Propeller. Propeller runs as a singleton. Effectively, there's some logic in there that uses the built-in Kubernetes leader election. So even if you have more than one Propeller running, only one will actually be doing anything. Admin and data catalog are basically user-facing services, so you can run multiple instances of that, and they're stateless. They just talk to one database. And this is actually what we ran at Lyft, which was the user-facing services were run on like a dedicated service cluster, and we on the team didn't have to really handle any of the infrastructure around that, and we just managed a series of basically data plane Kubernetes clusters, each of which runs one Flyte Propeller. And again, you have your collection of cloud-provided services on the right. And I think we've touched on all these. There's a new event pub subsystem, scheduling, notifications, Grafana, we saw the logo for earlier. Logging plugins was touched on. We've talked a lot about extensibility of Flyte and how everything is a plugin. If you wanted to extend Flyte, make it offer better support or more custom support, this is kind of a rough guide on how you can do it. It's roughly going in increasing complexity. So like the simplest thing that you can do is to introduce your own type inside the Python FlyteKit library. So if you had, say, for example, your own protobuf you can use, right? Or your own data frame type. You can write a transformer. All you have to do is tell the type engine how to convert to and from your custom types to the Flyte IDL literal. You can run a custom FlyteKit task plugin. What this is it means that the container that contains your code will still come up. It will still be run as a container task, And then you can just customize what that container does when it does come up. A backend plugin is one where you write a task and you declare it in the workflow in Python, but then come execution time, the task might not even have a container. So the canonical example for this is a query task. So instead of running a container, you run a query against a Hive, a database or something. And then you get the results, which the backend plugin will be responsible for writing and making known to the rest of the Flyte system. And beyond that, you can do, there's like some programmatic access to FlyteKit itself. So you can use that to to programmatically generate workflows and tasks and launch plans in FlyteKit if you wanted to make your own type of DSL. And logging plugins, this is undone in the backend to support different logging providers. Okay, lastly, we get a bunch of questions about how Flyte is different than some of the competitors. So this is a list of what we've compiled at a high level. It's fully containerized and K8s native. We think we have a pretty friendly SDK, Python and Java and Scala. The backend is highly extensible. Everything is versioned. We tend to use the Git SHA to version everything. You don't have to, but you can. And this makes things a lot more manageable and a lot more in line with the GitOps style of working. Horizontally scalable. We've used it extensively at Lyft and other places, not us, but Spotify has, executing millions of pipelines a month. You can execute a single task as a workflow. So you can just find your task in the task list and kick it off. You can have multiple schedules. The entire experience is serverless from the user's perspective, which is removes a lot of the infrastructure headaches that users formerly had to think about. Data lineage, caching, provenance, Grafana charts, operational visibility, like transparency into cost and being able to allocate cost across teams. And the pipelines are portable across clouds. So once you compile everything down to protobuf, you can then take those protobuf objects that define your tasks and workflows and take them anywhere to any Flyte installation, regardless of where it is being run. So, and yeah, that's it. That's it for the slides.